Hello everyone, we're continuing the topic of diodes and waveform shaping circuits using the diodes. Previously we saw how a rectifier circuit works and a limiter or a clipper circuit works. Today we're going to look at a peak detector circuit. Let's look at an example application of a peak detector circuit as a building block of a DC power supply. You've seen an application of a diode rectifier circuit in rectifying an AC input signal for the purpose of generating a DC output signal. So as you can see in this example, the output of this diode rectifier's two-port network is a pulsating output waveform. The pulsating nature of the output of this diode rectifier circuit makes it unsuitable for the purpose of a DC power supply. So in order to reduce this time variation at the output, we can use a filter circuit in here, and a simple way of reducing this time variation is to use a capacitor at the output of a diode rectifier and in parallel with the load resistor. So we can model these two blocks as a two-terminal load, and the capacitor is going to be in parallel with the load. So this whole circuit is going to act like a peak detector circuit, which we're going to look in detail and analyze the operation of this circuit. So going back to this block diagram, we have seen an example of a voltage regulator with a Zener diode in the past previously, and the Zener voltage reference, one of the benefits of it is that small variation at the input of this voltage regulator doesn't affect the output voltage, and you can get a pretty much constant output voltage waveform regardless of the small variations on the input signal to the voltage regulator. So let's look at a case of an ideal peak detector circuit in which there is no load resistor in parallel with the capacitor, and the only circuit elements that you have is a diode and a capacitor on the input signal. So this is an example waveform that is applied to this circuit. So this is my VI, and this is the same VI here. Assume at the beginning for t equal to 0, the capacitor doesn't have any charge and Vc is equal to 0. So this node is going to be at 0 volt and this node is at Vi. So when Vi is equal to 0, this node is at 0 and Vd, which I can label it this way. This is plus minus Vd. The voltage across the diode is less than 0.7 volts, and that the diode is going to be off. So Vi is gonna keep increasing until it reaches the value of the amplitude of Vd node. At that time point, the Vd, or the difference between this node voltage and this node voltage, is going to be equal to Vd node, and that's gonna turn the diode on. So the diode is gonna turn on, the capacitor is gonna start charging, and as Vi increases, the voltage across the capacitor is gonna increase as well until Vi reaches its peak value of V plus, and at that point this node is going to be at Vi and this node is going to be at Vi minus Vd node, and the voltage difference, the difference between two terminals of the diode is going to be equal to Vd node, but for any time point after that, the voltage, because Vi is going to decrease, Vd is going to be less than Vd node. As a result, the diode is going to turn off. So for any time point after this peak value, the voltage difference between two terminals of the diode is going to be less than Vd node. As a result, the diode is going to stay off. Now So Vi is going to keep increasing until it reaches the maximum value of V peak. At that time point, this node is at V peak, and this node is going to be at V peak minus VD naught. So you have VD naught volt across the diode, but immediately after this time point, Vi is gonna start decreasing, and the diff voltage across the diode is going to be less than VD naught, so the diode is going to stay off. So as you can see in this plot, after the capacitor is charged to a maximum value of V peak minus VD naught, the diode is going to stay off, and voltage at the output is going to stay at a constant value of V plus minus VD naught. So let's write the equations for the diode being on and off, and find out the equations for output voltage and the conditions of the diode being on and off. So when the diode is off, I know that ID is going to be equal to 0, and VD is going to be equal to and less than VD naught. Okay, so in that case, V out, using this KVL in here, I know that V out is going to be equal to VC, and that's a constant value. I'm going to label it with VC sub 0. It's a constant value. And VD is going to be equal to VI minus VC. That's my KVL in here. And I know that this is less than VD sub 0. From there, I know that Vi is going to be less than VC sub 0 plus VD naught. This is the condition for which the diode is off, and when the diode is off, V out is going to be equal to VC sub 0. VC sub 0 is the capacitor voltage at the moment the diode turns off. When it is off, the voltage across the capacitor is going to stay constant. Now let's look at the case when the diode is on. I'm going to use the circuit model for the diode for the case of diode being on, which is this symbol, a constant voltage drop equal to VD sub 0. So when the diode is on, I know that VD is equal to VD sub 0. And I know that ID is going to be greater than or equal to 0. So V out from the KVL in here and this KVL here, I know that V out is equal to VC, and that's equal to VI minus VD sub 0. So also I know that ID is the same as I that flows through the capacitor, and that's equal to C dVC over dt, and that's equal to C derivative of Vi minus Vd sub 0 divided by dt. That's equal to C, because Vd sub 0 is a constant voltage value, so I'm going to have C dVi over dt. Because ID is greater than or equal to 0, I know that dVi over dt must be greater than or equal to 0. So for the diode to be on, or in other words, when the diode is on, dVi is over dt is greater than or equal to 0, and using the KVL, I know that Vi must be equal to Vc plus Vd sub 0. In that case, diode is on, and I know that V out is going to be equal to Vi minus Vd naught, that's equal to Vc,